Hello everyone, welcome back to my YouTube channel. So today we are going to understand the k nearest neighbor, which is also known as a KNN. The k nearest neighbor algorithm is a popular machine learning algorithm which is used for classification and regression tasks, and it is very simple to understand. It relies on the idea that similar data points tends to have similar labels, right? So KNN is like finding the most similar items to make decision. To make it clear, let's understand a geometric intuition. So here, if you see, I have two features, f1 and f2, and I have plotted those points on the graph, right? So on this, if I ask simple questions, like if my data point lies here, right? Let me darker it, okay. So my data point is here, right? So what do you think? Which class level should it contain? So by seeing this graph, we can easily say this point also can be classified as a red point, right? Same if I point here, if let's say my point is here and I have to classify them. So what you will say? You can easily say this is surrounded by the blue point. So we can say this point can be classified as a blue point, right? Same. So KNN use this simple concept. So in KNN, K means number of neighbors you will consider, right? So for example, let's say my point is here, right? And K is equal to 3. So it will pick 3 nearest neighbor. So basically in this case, this is this point and this point, right? So these 3 points are nearest neighbor to my query point. So I got two red ball and one blue points, right? So from this, I will take majority vote. So there are majority points are red. So I will classify that particular point in a red class, right? Similarly, if my point is here, and let's say three neighbor nearest point are this one, and this one. So in this case, I will classify my point as a blue point because the majority neighbors are blue, right? So this is very simple fundamental of k nearest neighbor algorithm, right? Okay. So now we understand a k nearest neighbor concept. So let's understand what are the distances we can use to calculate the nearest point, right? So if we see, there are majorly 3 to 4 distances are used while we are dealing with the k nearest neighbor. So first is Euclidean distance, second is Manhattan distance, third is Minkowski distance, and four is Hamming distance, right? So we'll understand each and every distance in detail here. Okay. So Euclidean distance, you know very well, it is based on a Pythagorean theorem, right? So if I say I have to calculate the Euclidean distance from these 2 points, right? So Euclidean distance would be this distance, the shortest path, this line. Sorry, let me put it this way. So this will be simplest distance or shortest distance between these 2 points will be Euclidean distance, right? So Euclidean distance is formula, as we know. Let me write it down here. So it will be the distance is equal to x1 minus x2 square y1 minus y2 square and whole have under root. So you can write 1 by 2 formula raised to 1 by 2, it's also considered as a under root, right? So this is basically a Euclidean distance, right? So if we talk about the Manhattan distance, so it is like not taking a square, it is just summing this point, like, so let's see, Manhattan distance would be like this plus this. So this would be your Manhattan distance. So if I write the formula for it, it would be distance is equal to x1 minus x2 plus y1 minus, oh sorry, uh, sorry, I just selected a wrong tool. Yeah, so your Manhattan distance would be d is equal to x1 minus x2 plus y1 minus y2. Simple. So this is mode of that. Alright. So this will be your Manhattan distance. If we talk about Minkowski distance, so it is the generalized distance. So let me write the formula and then we can understand. Let me write it here. Right. So D is equal to, let's say, sigma I is equal to 1 to D mod x1i minus x2i mod raised to p raised to 1 by p. Right. So this is the Minkowski distance formula. So if I say, yeah, so this is Minkowski. So if you put 2, when replace 2 by p, it will be your Euclidean distance. If you put 1 instead of p, it will be your Manhattan distance. So you can put any number of them and it will generalize the formula. So you can say Minkowski distance is the generalized formula of Manhattan and Euclidean distance, right? So now let's see what is Hamming distance. So Hamming distance is basically used in the text processing kind of setup, or when there is a Boolean vector. So let's say I have two vectors 0 1 0 0 1, right, and I have another vector 1 0 0 0 0, right. So for in Hamming distance we will calculate how many points are differing, right. So here I would say this is 1 1 and 1. So the Manhattan distance will be 1 plus 1 plus 1 is equal to 3. So this is simple Hamming distance. It is basically used when there are Boolean vector or we are encoded our text into one hot encoding kind of setup, right. So this is our Hamming distance. So these four are the distances which can be used in a KNN. Okay. So let's move further. Yeah. So there are one variation in the KNN, or you can say enhanced version on KNN, which called as a weighted KNN. Okay. So see, for a query point Q, we have these 5 nearest neighbor. These 5 nearest neighbors are there. Okay. So 3 are red and 2 are blues. Okay. So if in simple KNN we have to classify them, we can easily say this point is red, right? But if you see carefully, the blue points are more closer to our query point as they have less distance, right? Instead of red. Just because they are majority, we are assigning a red label to our query point. But if you see, the blue points are more closer. So weighted KNN is a way to avoid this situation. So what we will do in weighted KNN, we use some weighing scheme. So simplest weighing scheme will be, instead of using distance, use 1 by distance while calculating a majority, right. So let's say in this case, for simple KNN we see it will be classified as a red, but what we will do in weighted KNN, instead of this simple majority, we will use distance based majority. So for red point we will calculate like this 1 by 7 plus 1 by 8 plus 1 by 9 red points, right? And for blue points we will do 1 by 3 plus 1 by 5 blue points, right? So here we will get, when you will sum this, we will get 0.378 red point, right? Sorry, let me erase this. So you will get 0.378 red points and let me write here 0.533 blue points. Yeah. So here you can see blue point has majority here, or more weights than the red point. So this point will be classified as a blue point, which seems logically and geometrically good, right? So this is weighted KNN. Okay. So now let's understand what is overfitting and underfitting in KNN, right? So let's talk about the underfitting first. So underfitting happens when your model is too simple to capture underlying patterns, right? In KNN, that can be occur if we choose a larger value of k. So if we choose larger value of k, it will consider more neighbors or more samples to decide whether this point is blue or red point, right? So it will not generalize. It will uh, underfit. It will not able to proper learn. So if we consider simple example, let's say I have 100 red points, right? Let's say 90 blue points, right? And I just took k is equal to, let's say, uh, number of samples we have. Let's say I have take k is equal to 190, the largest value which we can have, right? So if k is equal to 190, then KNN will always predict the majority class, right? Because if k is equal to 190, the model will use all points to predict, and at the end it will do majority voting, and majority class will always have larger number of points, right? So that means it is underfitting. It is not able to learn. As you increase the value of k, model tends to do underfit, right? Okay, so now let's understand what is overfitting. So let's say you have a k is equal to 1, right? So every time your model will select only one point to predict, right? So it will perform exceptionally well on training set, right? Because it is only considering one data point, right? So it will be best performance on training set. So it will be overfitting. It will not able to generalize the pattern or our data to understand new points, right? So it will be overfit. So in summary, if you increase the k value, model will tends to underfit, or if you use smaller value like 1 for a k, it will be overfit, right? So the key challenge is we have to find the best k value between the overfit and underfit. It will be achieved by cross validation and the hyperparameter tuning, right? So here k is a hyperparameter, as we can tweak that parameter while training the model, right? Okay, so now let's understand time complexity and space complexity of KNN. If we talk about time complexity, so time complexity will be order of n star d, right? So here d is a number of features we have, and n is number of data point we have. So basically in training there is no training happens in KNN, but KNN just simply store every points, right? So when there is an inference time or prediction time, it can calculate the nearest neighbor to query point, right? So space complexity, is depend on your dataset size. So as your dataset increase, your model size also increase. This is the major drawback of KNN, right? So training time complexity would be order of 1 because KNN is not training anything, it is just storing your samples, right? Okay. So now let's say prediction time or inference time. Sorry, let me erase this. Okay. So let's see inference time. Right. So on inference time or prediction time, KNN has complexity of order of n star d star k. So n is number of samples, d is number of feature, and k is number of neighbors we need to consider. Right. So if you break down this time complexity, so we can say order of n star d or n into d, it's basically used to calculate a distance from our query point. So we will calculate the distance of all points from our query points, then only we can find the best nearest neighbor, right? Top nearest neighbor, like, or k nearest neighbor, and k is to identify k nearest neighbor. If we optimize this, we can remove this k, right? But still the time complexity also will be n star d, right? So major drawback of KNN is KNN's time complexity and space complexity. So as your dataset increase, your time and space complexity also increase. So that's why, let's say if you have a millions of record and your dataset size is in GBs, right? Let's say 2 GB, 3 GB dataset you have, which is not so hard, right? It is a reasonable size. So your KNN will also have the size of 1 GB, 2 GB models, which is not good while you are inferencing, or when you have a low latency, you need low latency system or low space complexity system, right? So this is the major drawback of KNN. All right, so that's all about the KNN. Thank you for watching. I hope you now have clear understanding of KNN. In our next video, we will implement KNN from scratch in Python. So if you enjoyed this video, please like, share and subscribe to our YouTube channel for more this type of content. See you next time. Thank you.